I just hit, Alt Z, so that'll start it. If you'll check, make sure. Yeah, because we lost one of them. Yeah, we're good. Okay, so today we're going to be talking about the chemical fundamentals, which is partitioning. And when I say partitioning, we're splitting the analyte between the organic phase and the aqueous phase. So before we get to liquid-liquid extraction, let's refocus our efforts on equilibrium chemistry. So thinking about acid-base chemistry and controlling whether something is ionized or not using pH. So let's dive into that. It should be review. If you had a really difficult time with this in chemistry 2, at Chem 2, don't worry, because this will be the second or maybe third time you've seen it. And I found, for me, the third time is a charm. It really clicks then. So let yourself get it. Do not self-talk your way out of something by saying, oh, I never got this, I can't do it. Okay, that's the way to failure. Say, all right, I'm going to focus, try to understand the techniques that he's talking about, and I will get better at this. So in terms of sample prep, this is still used. Even though we have all of these instrumental methods, a lot of times you have a really troublesome sample. It might be a soil sample, and you don't want to test the silicates. You want to see what's absorbed in the soil. It might be a blood sample. Remember the external standards failed on that blood sample because you had all these enzymes in there that were metabolizing the cocaine? Well, you might be able to separate those analytes from all the other blood components and analyze them externally so that you don't have a matrix mismatch. Some are really easy. When the matrix is irrelevant, you just take the sample that you received and you dilute it and shoot it onto the instrument. But a lot of times that's not what happens in a forensic lab, because you have blood or urine or some sort of fluid from the body, and you need to get rid of all of the heavy components. You're not going to stick blood cells in the inlet of a GC. If you do, you're going to be spending a lot of time in maintenance after that, trying to unclog everything. So filter and wipe. A lot of times if you have powders, you're dealing with a wipe, you have to extract it from the wipe. And since you're doing extraction with a solution, you may end up doing liquid-liquid extraction, where you're trying to separate then the analytes. You're already having to separate it from a solid medium. Now you may want to use liquid-liquid extraction to concentrate your analyte in a different form. Homogenization. This is if you want to get something out of tissue. So if you think about tissue, it's mostly water, but all of the water, the aqueous solution, is trapped in these little things we call cells. And so you've got to disrupt those membranes to make it homogeneous. So they make these little ultrasonic things or these little hand blenders. And so you might take a tissue sample and homogenize it. You put this little hand blender in there and it destroys the cellular structure and releases all of the fluid. And then you can do a pretty low power centrifuge to separate all of the solid material down to the bottom, and then the supernatant will have all of your analyte material. And then there's lab sampling, taking things from a large seizure and then selecting small subsets that should represent the large seizure down to what would be a lab sample, and then you take from that lab sample your aliquots that you analyze. And so in all of these cases, well, I should say in many of these cases, we have to do partitioning. And we let Le Chatelier, remember Le Chatelier's principle? We put stress on the system and it reacts to relieve that stress. So if we have an acid-base reaction and we put in excess acid, we can drive the reaction to the products or drive it backwards to the reactants. And so I call that Le Chatelier's taxi. You can taxi us to one side or to the other. And so let's get refamiliarized with this. It's a way to get the analyte out of the matrix or from other interference. Let's say we have two mixtures. We have two analytes. One's a base, one's an acid. We can put that into a base and drive one to the product side and leave one as a reactant. And so this is using that equilibrium to drive partitioning. Let's go back to that generic equilibrium reaction or equilibrium constant. So if you have this generic reaction, the equilibrium constant is products over reactants, and then they're all raised to the number of moles. So you have the concentration of C And if you really need to review, that square bracket, that means the concentration of C. The concentration of C raised to the number of moles of C, and the concentration of D raised to the number of moles. And so this would be the equilibrium constant. And if you have a K that's much greater than 1, that means the numerator is larger than the denominator. So that means the products are more abundant than the reactants. And so then the equilibrium lies to the right, or products dominate. If the equilibrium constant is much less than 1, then reactants dominate. And we can push this reaction right and left today using pH. Your body does the same thing. Your stomach is very acidic, so it has a very low pH. It's going to drive that reaction one direction or the other. And so we use acid base to drive solubility. And then sometimes you have redox equilibria that are useful. Many of the breathalyzers work on a chromic, like a dichromate oxidizing agent that oxidizes the alcohol. And so you can breathe into that, and it's a redox reaction. And then it has a color change inside the instrument that can be detected and give you the concentration of alcohol in your breath. I don't exactly know how they calibrate how much volume you've blown into it, but that's part of their engineering in figuring out what the concentration of alcohol is. Let's go through a survey of pH just to review things. People talk about how bad Coca-Cola is for you, right? What are some of the nasty things you've heard about Coke? It what?
It corrodes your teeth.
It corrodes your teeth. What else? You've seen these email scares and things on Facebook. Y'all haven't heard any of these? Really? Okay. You hear these scares. Don't drink Coke. If you put Coke on like hamburger meat, it'll totally tear it up and destroy it. If you clean the corrosion off your battery. It cleans the toilet. Yeah, you have all that stuff in there, and the Coke will just chew it all up. And yes, if you look on the side of the Coke, it says phosphoric acid. It's buffered. Okay. And it might have a pH that's, here it says Coke and vinegar, between 10 to the minus 2 and 10 to the minus 3 acid concentration. So between 2 and 3 pH, you say, whoa, that's really acidic. But when you drink Coke, where does it go? In your stomach, and gastric juice is a pH of 1. Yeah. So if you threw up in the toilet, that would clean it too. Right? Or if you threw up on a piece of meat, it would chew it up because that's what's happening in your stomach. So yeah, Coke does it, but your stomach does it even better than Coke. So these people that are trying to scare you, and I guess it would probably harm your teeth too, but you definitely brush your teeth if that happens. So yeah, acidic scales, you don't need to be afraid of drinking Coca-Cola. Maybe you should be afraid of some of the other things that are in there, like the aspartame and things. But so there's fruits and vegetables. We see wine, tomatoes, bananas, black coffee. Those are all from slightly acidic to a little more acidic. But right there in neutral range is human blood, tears, looks like egg whites and milk. All these biological substances, these fluids in our bodies are buffered to be pretty near neutral pH. But the stomach is buffered to be a very acidic medium, and that helps break down food. And then as it goes into the small intestines and the large intestines, the pH gets higher and higher. And once you get into the colon, it's even above 7. It's close to 8. And so your body is set up to where it can absorb some things in the stomach and absorb other things in the small intestines and in the colon. So it's an amazing thing. We can take in bases in our stomach and take in acids in our colon. And so there's different places where the drugs will show up. And then pharmaceutical companies know this. And so they will find like time-release drugs. They want those to be soluble in a more basic medium, so it takes longer for that drug to be absorbed, and you spread out the effect over a long period of time. Fast-acting drugs, you want those to be soluble in the stomach. And so we'll see some of that today. Polyprotic acids. Now, if you look at these, there's a table of some polyprotic acids, and if you'll notice the exponents, citric acid is great. You got 10 to the minus 4, 10 to the minus 5, and 10 to the minus 7. These are actually a little close together. But most of the time, they're at least 2 orders of magnitude apart, like here, from 2 to 5. And so the nice thing about this, even though we have polyprotic acids, we have multiple protons on there that can come off, because of the different Ka values, they come off one at a time. So this is a marvelous thing for us mathematically, because we just really have to deal with one equilibrium at a time. So we'll pull one proton off, and then there'll be a period of nothing happening in terms of pH, and then as you raise the pH, then another proton will come off. And so at low pH, let's sort of test your knowledge again. At low pH, are protons abundant or not abundant at low pH? Low pH is acidic, so does that tell you that a proton is abundant or not abundant? It's abundant. So you have lots of protons at low pH, and so all your acids are going to be fully protonated, which in this case means they're neutral. So the species written over there on the left, those are all at very low pH. As you raise the pH, you start to strip off a proton. And you do that one at a time. So way over here is the fully ionized species. So far to the right, at high pH, all of these acids have had their protons ripped off and they've gone to other bases. And so then they're fully ionized. So for all of these acids, the most soluble form will be far to the right in basic media, because you've pulled off all of the protons, and now these are organic molecules, so they're not really soluble in water on the left side where they're fully protonated. It's when you've pulled the protons off and now they're ionized things are soluble because water stabilizes those ions. So that's the number one key this morning, is that ionized things are soluble. So let's go through an ice table review. Up here is written the problem: calculate the pH of a 2 molar solution of amphetamine, and they give you the pKa. Now, what do you see in that word, amphetamine, that gives you a clue as to whether it's an acid or a base? Amine. What are amines? Mm-hmm. So amines are bases. They take on protons. And so what we have for this reaction here, B plus water gives BH plus hydroxide, is we have a basic reaction. But we're given the pKa. It's just traditional that we list pKa's for everything, okay? Even if it's a base. And so this is a base, but you're given the acid dissociation constant. So that's actually Ka for BH plus. That's the Ka value for BH plus. But we have it written to where the reactant is B. So we're going to want to know BKB, not Ka. And so this is that relationship. If you don't remember that, write it down. Kw is equal to Ka times Kb. And you should know off the top of your head what Kw is. And it's 1 times 10 to the minus 14. Okay? So Kw is 10 to the minus 14. And that's where your 14-point pH scale comes from. Now, if you take the minus log of that, we use that so often in these calculations that we've given it its own name, P. So pKa is the minus log of the Ka value, and pKw is the minus log of the Kw value. And so pKw is equal to pKa plus pKb, because a log of two things multiplied by each other is the same as the sum of those individual logs. So we can split that out. We have Ka times Kb. If we take the minus log of that product, we can pull it apart and say it's the minus log of Ka plus the minus log of Kb. All that means is that your exponents all add together. So Ka is, in this case, would be 10 to the minus 9.8. So pKa here, 9.8. This right here goes there, 9.8. And pKw is 14. And so then we can find pKb. And so you just subtract 9.8 from 14 and you get the pKb. And then if you want to know what Kb is, then Kb is 10 to the minus p kb. So that's the antilog. Okay. So everybody with me so far? Just dealing with Ka values and Kb values is a big deal, because if you get that wrong, the whole thing is off. So let's look at what we end up with that. You could do it the other way, like I've done here on the board. You have 10 to the minus 14 divided by 10 to the minus 9.8 gives us 6.31 times 10 to the minus 5. So that is the equilibrium constant for the reaction that I've written. I wrote the reaction as a basic reaction, and so we need Kb to govern that reaction. So now we know the equilibrium constant, and then we have products, BH plus concentration times the OH minus concentration divided by the base concentration. Where is water? Why is water not in this? Review question. It's a liquid, and it's a liquid and it's a solvent. It's two things. Okay. So think about these concentrations. That's the concentration of BH plus in water. That's the concentration of OH minus in water. That's the concentration of B in water. And if we were to include the concentration of water in water, it'd be a constant. So that constant is just looped into the other constant. So all of our Ka values, Kb values, they already contain that constant value of water in water. So it's in there, but it's buried in the constant. So when we tabulate these constants, we've already taken that into consideration. So if we were to include it again, you'd be off. Okay, so we ignore the water part of these reactions. So then we set up our ice table. We have a 2 molar solution of our base. So if we sort of imagine initial conditions of 2 molar concentration of base, 0 molar concentration of BH plus, 0 molar concentration of OH minus, and then what's the change? That's when we do the X's. And so the X's have pluses and minus signs in front of them, and where do they change sign? Notice the one on the left is a minus, and the ones on the right are plus, but why do they change sign where they change? It's products and reactants. So right where you go from reactants to products, then the signs change. And so if we lose reactant, we gain products. And so that's what the plus and minus signs stand for. If you had coefficients in front of any of these in the reaction, then they would be in front of the X's. So if we produce 2 products or 3 products, like 2 BH plus, then it would be a 2X. And so then at equilibrium, we have the initial, and the change gives us our equilibrium. So we have 2 minus X, and then we have 0 plus X and 0 plus X. Now we're making an assumption here. We're saying that 2 minus X is essentially 2. Remember our significant figures when we're adding and subtracting? So when we're adding something that's really small, it's way down there in the decimal place, and we could add it, but then when we round, it's going to disappear. We only have our pH of 2.00. Okay, our concentration is 2.00. So we only know this to hundredths of a molarity unit, and we're saying that X is way below that hundredths. So we can't tell that we've added any X. This greatly simplifies the math. We don't have to use a quadratic formula when we make this assumption. So everybody's happy about that. Okay, so then we set up that equilibrium constant expression now with X squared in the top. So these two pieces were both X, and they became X squared. The base is in the bottom, this 2 here. And then the Kb. So that's our equilibrium constant expression. We can move 2 over, take the square root. Now what we're going to end up calculating, we're asked in the problem to calculate the pH, but we're doing a basic reaction, so we're going to actually get the concentration of hydroxide. And if we take the minus log of that hydroxide concentration, we get the POH. Well, the pKw is equal to the pH plus the POH. And so whatever we end up with for the POH, this is 14. And so the pH and pOH add together to equal 14. So our hydroxide concentration is, if we move the 2 over, so we have 2 times our Kb value, and then it's x squared, so we take the square root, and that equals x. And that's the hydroxide concentration. So this is our concentration of hydroxide. We take the minus log of that, and we get 1.949. And that will be an answer on the test. But that is the wrong answer. So don't sit there and look and say, oh, I got one of the numbers, therefore I'm right. You've got to know what you're calculating. Okay. And so that's the pOH, not the pH. So I subtract that from 14 and get 12.05. That will also be an answer. And that's the right answer. It pains me to do that, but I want you to be confident in what you're calculating, not on what you see as far as one of the possible answers. Okay, so then this is the most basic, too. It's one of the most basic problems that we'll do. Let's turn up the heat a little bit and do a quadratic formula one. Okay, so now instead of 2 molar, we have 0.0025 molar. So really tiny concentration. And so we have our ice table. The initial is 0.0025 and 00. Then we have the x's. And so now we have this 0.0025 minus x, and then we have the plus x's on the right. And I don't want to assume, since that's such a small concentration, I don't want to assume that it's insignificant. Okay. And so we're going to have this full equilibrium constant expression up there without any assumptions. So we need to get this in the standard form for a quadratic formula. So we need to get rid of that denominator by moving it over to the left, and then we need to rearrange so that we have 0 on one side, x squared, x, and the constant. So we've moved things around a little bit. We moved the 0.0025 over to the other side, and we just reversed everything, so x is on the left. And then we're going to put it in standard form. So this is the standard form where we have a in front of the x squared, b in front of the x, and c is our constant. And so this is the form we need for the quadratic formula. And so go back and review that. Make sure that you can write that out. Now the interesting thing about the quadratic formula is we have 2 results, potentially. Okay, that's plus and minus. So how do we take into consideration? Well, we'll put a little plus down here by the x when we calculate the plus value, and a little minus when we calculate the minus value. So we'll say 2 roots. So we'll say the x plus root. And so this is the x plus root where we insert everything, and we're using the plus sign. And so we have b, which is right here. All right, so that's minus b, and then that same thing squared, and minus 4ac. So a is 1, so that's nice. And then c is over here. Do not lose that minus sign. Okay, so that's right there. You lose that minus sign, and a lot of times you can't take the square root because you have a negative number under the square root. And you're like, uh-oh. So that's a big indicator that you've done something wrong if you get an imaginary root. Although sometimes you can have imaginary roots, you won't have it in these problems. And divided by 2a, so a is 1, so divided by 2. So we get this concentration of 0.000367. Now let's do the minus root, so x minus, put in all those numbers, only we have a minus sign here. So I'm going to circle those 2 things. And we get negative 0.000430. So this is pretty clear which one is the good one, because a negative concentration is nonsense. So it's like a vacuum for amphetamine. You get any amphetamine near there is a vacuum, and it sucks it in. It's negative 0.4 millimoles. No, so we use the 0.000367. And so then we take the minus log of that, and that's our POH, 3.44, and then subtract from 14, that's our pH. So it's 10.56, whereas before it was 12 point something. Okay. So it's a lower pH because, I mean, it's not as basic because we have much less base. So let's just check our work, right? We said that that 0.0025 minus x, that the x might not be insignificant. And so if we put that 0.367, you see that it didn't stay 0.0025, it dropped to 0.0021. So it was significant. So we shouldn't have done, assuming x was 0 compared to 0.0025 would have been wrong. It would have given us erroneous results. Okay. And so we have x here and x there for the BH plus and the OH minus. And so it's about 14% ionized. Do you remember how to calculate percent ionized? You look at the species here, and you have an ionized form, the BH plus, and you have the unionized form. And so it's the combination of both of these. It's this amount plus that amount is the whole, that's in the denominator, and then this amount is in the numerator. The ionized component divided by everything that's related to B. Well, we have everything related to B. It's 0.0025. That's what we started with. So it's 0.000367 divided by 0.0025. And that will tell you the percent ionization. Now, if we want this to go into solution, it's not going to be great because only 14% of it is soluble. You see what I mean? We're trying to, if we want to get all of it in solution, we need to put it in a pH environment where it's all ionized, not just 14% of it. Okay. We want all of it to be ionized. So that's when we start using buffers. We start using acid buffers or base buffers to drive that taxi to one side or the other. We don't want it anywhere in between. So this is speciation driven by Le Chatelier's taxi. We're pushing this all the way to the products because we want the products. Let's say BH plus was what our spectrometer detects, and so we want all of it as possible, as much of it as possible. So we're going to put this in an acid buffer. And now I've changed the reaction a little bit. Notice I've taken my base here, B aqueous, and put it in with acid to generate my protonated base and water. And so now here's where the arrow is. That's where the pluses and minus signs are going to change in terms of x. And so I have my reactants, minus x, and my product, plus x. And so this is in a pH of 2. So the concentration of acid, H3O plus, is equal to 10 to the minus 2.00. So that's where this number came from, 10 to the minus 2. Okay. And you should be very quick with that as well, going from pH to acid concentration and back. Now, it's really nice if it's a nice even number like 2, because it's 10 to the minus 2, 0.01. What a pH 1 is, 10 to the minus 1, or 0.1. A pH of 3, 0.001. pH is 7, 0.000001. Okay. What if it's a pH of 2.5? It's between 2 and 3, right? So it's between 0.001 and 0.0001. So you could say 0.0005, which is halfway between. Okay. Won't be exactly, but that's a good estimate. So you should be able to look at those powers of 10 and estimate. That's a handy skill. So then looking at this, what we're going to do, this is the best use of Le Chatelier's taxi you'll see. We've put this in the acid, and so what we're going to do is we're going to swing this all the way to the right. So we want this to swing all the way to the right. So I want this to go all the way to 0. And if this goes all the way to 0, then what is x? 0.0025. And so if I have this minus 0.0025, I get that, 0.0075. And this plus 0.0025 gives us 0.0025. So that is not an equilibrium calculation, that's a new initial. You see what I'm writing there? New initial. I've thrown it all the way to the right. And I've said, even though nature never really does this, I can do this on paper. I can say, let's take this reaction 100% to the right. And then have it come back a little bit. Because it's not going to come back very much. I'm trying to avoid the quadratic equation. Is everybody with me on that one? Let's avoid that thing. It's prone to error. It's not that it's hard, it's tedious, and you're going to drop a negative and screw something up. Okay? So let's go all the way to the right and then come back, because it's not going to come back very much, and that X amount that it comes back is going to be insignificant. So then we can avoid the quadratic formula. So the new initial is what I've written down, and now we have new changes. So this will be an ice table down here. So this right here is an ice table. This up here is just swinging it with Le Chatelier's taxi. Okay. And so now I have swung it all the way to the right, and I have 0.0025 minus x is going to be 0.0025. That is going to be a tiny, tiny x, because we have so much acid on the reactant side. And 0.0075 is not going to gain much acid back, because it's not going to swing back to the left very much at all. But 0, anything added to 0 is significant. So we have to keep x there. But in our final formula, then, we're just going to have 1x, no quadratic formula. Let me pause right here, because this is mentally something that you might need some clarification on. So chew on this and raise your hand.
I think the range is determined when to drop.
The good question, when do we think x will be significant or not, right? Look at the first two rows, okay? I've got 0 product, the first row, 0 product, and a whole bunch of reactants. And so x is going to be big. It has to be. You see that? And so we can't say that x is insignificant. Anytime we do that simplification, we're doing that simplification because it doesn't move very much. Do you follow that? Like in the previous ones, like the very first one we did, we said x is really small. We have a pH of 2, and we've got a lot of base, and it's not going to go very far to the right, you know, because if it goes a little bit, x is small compared to such a large amount of base. Well, now we have a large amount of base, and we have a large amount of acid, and that acid is going to push it all the way to the right, or a long way to the right, and so we're going to have a big x. So we're going to have to keep x in both of those calculations. We can't say x is insignificant in the first two rows. So if we know x is going to go far to the right, let's take it all the way to the right. So that's all we're doing, is we're saying if it's going to be big, let's go big. And let's take it all the way to the right. And now, if it tries to come back at all, it's trying to create more acid. And we already have a lot of acid. So it can't really push back against that much acid. See, look at the new equilibrium, or the new initial here. If this tries to come back, it's going to produce acid, and there's already a lot of acid. So it can't come back because of that number. And so this is insignificant change. We lose an insignificant amount of BH+. We gain an insignificant amount of acid. And then we do gain a calculatable amount of base, because we've pushed it all the way to 0. So it'll come back a little bit, and this will tell us how much it comes back. Okay. So let's, and y'all can go back and watch this video over and over again and hear the explanation until it clicks. It will click. If you just walk your way through this section over and over again, you'll see what we're doing. So this is our equilibrium constant expression. We have that same pKa, so it's the 10 to the minus 9.8. And this is written in in this form with the X. We've got the BH plus now. Notice this is going to potentially be confusing. So we have BH plus here. This is our reactant because we're going backwards, right? And this is an acid. So we use that pKa value. And we're using Ka, and that's equal to the hydronium ion concentration, the base divided by BH plus. So this is our equilibrium constant expression for this reverse reaction. And so solving for X, it's 10 to the minus 11 moles per liter of solution. So it doesn't come back very far at all. I mean, it's calculatable because we're comparing it to 0. So it's not 0, but it's incredibly small. We didn't need to use the quadratic formula because we swung it all the way to the right and then looked at the reverse reaction. Okay. So what's the percent ionization? We started with 0.0025 moles per liter of base. We now have 0.0025 moles per liter of the ionized form. And so it's 100% ionized. And that's what we want if that's what we're trying to analyze. If our spectrometer is sensitive to the protonated form because of a color change, kind of like phenolphthalein does, you know, it's colorless or purple. And so we want to swing it all the way to the colored form so we can detect it. Having it 14% colored is not good. Plus, that's really fluctuating a lot around that region. So we want to swing it all the way to the end so that it doesn't fluctuate much at all. Or in this case, if it was a drug and we want it to be absorbed, where would it be absorbed? You know, it would be absorbed in acidic medium. So bases would be absorbed in the stomach. So we can look at that. Where are things absorbed in the body? There's a pH 1 to 3 for the stomach, 5 to 7 for the small intestine, 7 to 8 for the colon. So things are going to be absorbed in different areas of the body. And so bases are protonated in the stomach, and that makes them more soluble. So think about when something is ionized. When bases are protonated, they've received a proton, which is positively charged. So bases are ionized when they're protonated. Acids are not. Acids are neutral when they're protonated. So you can't say protonated things are soluble. It's ionized things are soluble. Okay. So when you protonate a base, it becomes ionized, and that makes it soluble. And then acids in the basic medium of the colon are deprotonated. That makes them anions, and the anions are what's soluble. So you've got to follow what's ionized, not what's protonated or deprotonated. That's how you figure it out. But in terms of solubility, it goes with the ionization. So we can look at drug absorption. Let's look at this drug that has a pKa of 7.6. It's a phendimetrazine tartrate. Notice how some of these drugs, they have an anion like tartrate or citrate put on them, or sometimes hydrochloride. Those are indicators that that drug is a base, and they've salted it out. They've put a proton in there and an anion. And so notice that tartaric acid up here has lost a proton. It's gone on to the base. And so that made the base a cation and made the acid an anion. And this is the drug. They just coupled it with the tartrate to make a cation-anion pair, and it'll salt out if you have it in organic medium. So once you have ionized species, they're not very soluble in organic solvents, and so they'll make crystals. Remember from organic, you do recrystallization, you start growing these crystals in hexane or what have you. It's because it's made a salt, and it doesn't want to be in solution. Organic solvents can't stabilize those ions. So they find each other, and they may crash out in terms of tiny little crystals, or if it happens slowly, they might grow some nice needles or plates. Okay. And so a lot of these drugs have been salted out of organic solvent. It's kind of amazing when we get to the chemical evidence. They don't, I mean, these are a lot of times clandestine labs. They don't have access to our nice, clean, pure toluene and hexane. You know what they use? Gasoline. Coleman fuel. So people are ingesting stuff that was recrystallized in gasoline. Yeah, not cool. Okay, so anyway, so side, yeah. So it's kind of gross. I mean, as if the drugs wasn't bad enough.
Right.
It's sort of funny that we're disgusted by the gasoline more than the drug. So let's look at this. We have the BH plus in this case, reacting with water, making the base, and hydronium ion. And we're putting it in a pH buffer of 1.0. So the stomach, if a base comes in there and takes away some of those protons, what does the stomach have? It has a little acid pump. It sticks out, like the little commercials for Nexium and all those things. This is pumping out the acid because your stomach, the stuff in your stomach is using up the acid, and so it's buffered for real. And it's not just buffered, but also it's replenished. And so you're not going to change the pH of the stomach. Well, yeah, that's what I guess acid reflux and those kinds of things are doing. You're trying to milk of magnesia or Tums, or you're trying to adjust the pH of your stomach, but it's very difficult to do, because your stomach is putting out a lot of acid. And so we have some of the base reacts with water and forms the deprotonated base and more hydronium ion. But that's hard to do, right? So it's pH of 1, okay? And so it's 0.1 plus X is still just 0.1. The amount of base that is lost is insignificant, so it's 1 molar. And then we have this 0 for the deprotonated form. Anything added to 0 is significant, so we keep that. And so we're going to stay 100% ionized in this case. We could solve for that X if we want to. So we've set up this equation. We have the pKa is 7.6, so that helps us calculate Ka. We have X from our table, 0.1 over 1. And so we end up with 2.5 times 10 to the minus 7. It's always good when you calculate X to just check your work. Is this insignificant compared to this? And the answer is yes. So 0.1 plus 2.5 times 10 to the minus 7 is still just 0.1. And the same thing over here, 1.00 minus 2.5 times 10 to the minus 7 is still just 1.00. So you can always kind of check your assumption. Say, I assume X is small, I don't really need to care about it. And then you calculate X, you can go back and look and say, was I right? And you can say, yeah, it's a good assumption. So this base would be 100% protonated in the stomach. What about in the colon, where we have a pH of 7.6? So the same kind of reaction, although now we have the hydronium ion concentration is 10 to the minus 7.6, which is 2.5 times 10 to the minus 8. So because that's a buffer, it's going to be unchanged. I said stomach, I think I meant colon. So it's going to be unchanged. So if anything tries to change that 2.5 times 10 to the minus 8 acid concentration, the colon is going to react and make sure it stays the same. So in buffered problems like this, it's really pretty easy. The hydronium ion concentration doesn't change. If we lose any acid form of the base, it's insignificant. Okay. Actually, we're going to keep that X. Let's just see. So we've set up our problem. Now this 7.6 is not the pH, although it equals it, but it's just coincidental. So that's the pKa for this base right there. Okay. And this is from the pH. And this one looks like we might need to use the quadratic formula, but coincidentally, this number right here, 10 to the minus 7.6 is 2.5 times 10 to the minus 8. And so these cancel. That's convenient. So there's a 1 on the left, an X on the right, and 1 minus X on the bottom. So I'm going to bring this 1 minus X over to the left. And then I'm going to bring the X back over. So I'm going to have 1 minus X is equal to X, or 1 is equal to 2X. or x is equal to 0.5. Okay. And so now we put in x as 0.5 over here. So 1 minus 0.5 is 0.5, 0 plus 0.5 is 0.5, and that all matches our equilibrium constant expression, and so it's 50% ionized. So essentially we've proved that when the pH equals the pKa, we're 50% ionized. Okay, which is a principle that we had in terms of equilibrium chemistry that you might have remembered. But so this drug is going to be 50% ionized in the colon. Now it will still be absorbed, but it'll be slow. Okay, why would it still be absorbed? Why wouldn't just half of it be absorbed? Because remember, the ionized piece is soluble. And so you would say half of it is soluble, so half of it is going to go into the bloodstream. Why doesn't it stop there? Yes, so then the part that wasn't ionized is missing the ionized piece, and so the equilibrium is reestablished, and half of that goes into the bloodstream. So now 3/4 has gone in, and then it's reestablished, and half of the remaining amount goes in. But you see how that's slower? It's going to be some exponential absorption that's related to the kinetics of the reaction, and so it's going to go into the bloodstream slower, half at a time, as opposed to being 100% ionized and all of it going in. So let's talk about percent ionization. We can simplify these things. This is the percent ionization equation in the upper left. And I know that I've got A minus over here and HA. I've got a couple of A minuses, and all I really want, I want to compare it or insert it over here. And so I want something in the form of just A minus over HA. So I just want something like that. So I can rearrange this. Let's flip this over. And now that I have this species in the denominator, I can split it apart. And I can have HA over A minus and A minus over A minus, which is 1. And so this is nice. I've got just this piece right here. So let me solve for this piece so I can stick it into my Ka equation. So HA over A minus is 1 over the percent ionization minus 1. So now I can use this little piece, this fun little piece, in my Ka expression. So I take the minus log of Ka, and I get pKa. The minus log of hydronium ion concentration is pH. And then the minus log of this reaction, I'm just going to leave as minus log. So I have minus log A minus over HA. And I've got this over here. One's upside down from the other. But let's also rearrange this. I have pH here, and I want to put the minus log on the other side. So I'm going to have a plus log and a Ka, and I'm going to flip the whole reaction. So pH is equal to the pKa plus the log of the base over the acid. And that's the Henderson-Hasselbalch equation that you may have seen from Chem 2. Okay. It's amazing. They just took equilibrium and did 2 steps on it and got an equation named after them. That's not right. Okay. And so then we have this A minus over HA, and it's a plus log. If I change that sign, I can flip these two, right? So if I take a minus log, I have HA on top. Well, with HA on top, I can put this piece in there. So this can go over here. And now I have this equation with my percent ionization in it. But most of the time in the problems, I'm given a pH, like the stomach or the small intestine or the large intestine. So I have a pH. And I've given a drug, say amphetamine, and I go to the Merck index and I find its pKa value. And so I have the pKa and I have the pH, but I don't have the percent ionization. So I'd like to solve for the percent ionization. So let's get this guy out of that bottom of that log. It's kind of buried in there. Let's pull it out and write it in terms of the others. So I'm going to move the pKa to the other side, and let's change the signs and everything. And now I want to get rid of that log. So it's going to be 10 to the whatever. Okay, so 10 to the pKa minus pH. That got rid of the log. And now I'm going to move that 1 over to the other side. So I'm going to have a plus 1 over here, and I'm going to invert the whole thing so I can solve for that percent ionization. So percent ionization is 1 over 1 plus 10 to the pKa minus pH. Now that's a whole lot more algebra than Henderson and Hasselbalch did, so I think I deserve something. Okay, that's not recognized by anybody but me. But still, so anyway, that's a handy little tool for if you have the pKa of a substance, and and it's an acid. This is all based on acids. HA going to A minus. Okay, then this will give you the percent ionization. So this is just a form to show that comparing pKa and pH, when they're equal, then it's 50% ionized. We established that. When they're equal, it's 50% ionized. But when the pH is higher than the pKa, it's more basic. High pH is basic. And so you're going to have anions. You're going to deprotonate all of your acids, and you're going to have 100% ionization of the acid. And it's typically 2 orders of magnitude or 2 units of pH. So if you have a pKa of 5, pKa, listen carefully, pKa of 5, if the pH is 7, you have 100% ionization. They're all anions. 5 to 7, that's 2 orders of magnitude. Really, 1 will do it. If it's a pKa of 5 and you have a pH of 6, 100% ionized. Okay, but 7 is really safe. Okay, what if I have a pKa of 5 and I have a pH of 4 or 3? 0% ionized because it's so acidic. It's a low pH. It's acidic, and all those acids are protonated, and so that means that they're neutral, which means they're not ionized. Okay. Now, if this is difficult, then don't try any of these shortcuts. Just go back to the ice table. Okay. But if you're confident in thinking through the problems, I've got an acid in an acid environment. It's protonated, neutral, and not soluble. If I have an acid in a basic environment, it's deprotonated, ionized, and soluble. The problem comes when you use pKa for a base. Because in this little equation, the Williams equation, was developed with HA and A minus. The base is B and BH plus. Never worry, use the pKa and just take 1 minus that. So if it's a base, you can use the pKa, but you better subtract that percent ionization from 1. Okay. And this would mean that low pH would protonate bases, make them ionized, and make them soluble. Let's pause just 1 minute for any clarification on that. We'll get a little bit more practice when we do liquid-liquid extraction. These are the kind of things I want you to be fast with, because that's going to be helpful. Okay, now what if you have a thing that's amphiprotic? It's got a little bit of acid and a little bit of base. It can protonate, act as an acid, or it can be protonated and act as a base. When you're in between those two pKa values, a lot of times the proton has been lost to its own base. And so you have a zwitterion. Like think of glycine or all the amino acids. Okay? The acid proton has hopped over to the base. And so you have an acid anion and a base cation in the same molecule. And so when you're in between those two pKa values, you actually... it's very soluble, and so you would have this ion be what am I trying to say? The ion would be very soluble in those cases. And so let's go through our exams, and we'll finish up. Brittany Blanco. Brittany? Brittany? Brandon? Catherine? Jared? Cody. Logan. Newman, here, Mauricio. Brenda. Sarah. Elisa. Josephine. Catherine. Yvette. Brianna. Molly. Teresa. Alex. Tracy. What's that? Williams and I'm always last. Okay, let me give you a couple of things on the analysis spreadsheet.